In this lecture, we are going to talk about the closed loop gains of the operational amplifiers, like inverting amplifiers and non-inverting amplifiers. So these are the topologies you want to use for your applications, like amplifying the signal from the sensors, things like that. Okay. So closed loop gain. Of the inverting amplifier and the non-inverting amplifiers. That's a part 2 of this lecture. Okay, so let's look at the inverting amplifier first. If I draw a topology like this, minus plus, here's Ri, here's Vi, here's Rf, which is a feedback resistor, here's Vo, and that's ground. So what's the voltage gain for this topology? So voltage gain means what is VO over Vn or VO over Vi, right? We just want to know how much this amplifier can amplify our Vn because it's too small for our ADCs or all these following circuits to detect. So we need to amplify it first. Okay. So now what's the gain here? What's the closed loop gain here? Okay. So the way to derive it is like this. We know the voltage here is 0, is at least close to 0. So we are treating the voltage here as 0 volts. And because all the amplifiers has a very huge input resistance, right? So none of the voltages are getting into the amplifier. So there's nothing after this node. There's nothing, no current getting in there, getting inside. It's not accepting any current from the outside. So the current is going to flow in this way to the output. During the calculation, so when you are calculating, you just do it this way. But you need to know, because this is a lower voltage and VO is normally a slightly higher voltage, so it should be actually higher than here. So physically, there's a current go into the junction in this direction and another current going into the junction in this direction. But since we are just trying to model the current, so we just define the currents flowing that way, which it doesn't matter because you just have a different, so all the currents are vectors, right? So we just draw the current flow in that way. And because the current flow inside the junction equals to the current flowing out from the junction. So we are getting Vi minus 0 volts over Ri equals to 0 volts minus Vo over Rf. This is what we know from this circuit. Okay, and then you can get Vi over Ri equals to minus Vo over Rf. So Vo over Vi equals to minus Rf over Ri. That's the closed loop gain for this this inverting amplifier when, don't forget this, when AV is infinity. And we're going to derive the equation for the gain, closed loop gain for the non-inverting inverting amplifiers whenever the open loop gain of the op-amps are finite. But now we are treating all these guys are ideal. Ideal op-amps. So this is for inverting. So what about non-inverting? Non-inverting, which means the signal is going to be injected to the non-inverting terminal. So if you draw it like this, still we have the inverting terminal on the top and the other one at the bottom. It looks like this. Signal is going to be injected here, plus minus. This is V in, This is VL, this is RF, this is R1, and this is grounded, right? But normally, this is fine, but normally we are going to flip it so it looks better. And this is also the topology you are going to see the most often times. There's no difference, okay? It's just trying to flip it so make all the input signals on the top. Okay, that's VO. No difference, right? So how to derive VO over V in? This is what we are interested in, right? We just want to know how much times this amplifier, this closed loop configuration topology can amplify my V in. Okay, so still AV is infinity, so it's an ideal amplifier. So VP equals to VM. Keep in mind, VP equals to VM. So in that case, VP equals to VM. So what is VM over here? We know this is VO, this is ground. So this is literally a voltage divider. So VO times R1 over R1 plus RF equals to VM, right? Voltage divider over here. And VM equals to VP equals to V in. All right, so it's pretty easily like you can find out a relationship between VO and V in. Because this entire thing is VM and this is also VM, you can just put V in here. So what you're getting is VO times R1 equals to V in times R1 plus RF. Right, just substitute V in over here, right? Because this V in equals to VM. And then you move V in times R1 to the left, so you are getting, oh no, so because you already have V in, V out on the two sides, so just directly divided by V in on two sides, so you are getting V over V in equals to R1 plus RF over R1 equals to 1 plus RF over R1. So this is a closed loop gain for an ideal non-inverting amplifier. Okay. And we still have to think about the cases that the op-amps are not ideal. Then what's going to happen? So now let's take a look at that case. So what if the open loop gain AV is not or is finite? Okay, then the result will not be that accurate if we're calculating the output voltage using all these conclusions over here. So we'll see why. Okay, so let's look at the inverting topology first. Okay, so we have VP, VM, because AV is finite, then what? VP is not VM anymore. All right, keep in mind. Then you have to calculate everything individually. So the first thing you would know is you still have this kind of current flowing inside the circuit from V into VO, but the equations will be different. So let's list the first one first. It's just one current. So what we know for sure here is it is still one current, So we can list one equation really quickly, no problem. So Vi minus Vm over R1, which is the current here, equals to the current here. Vm minus Vo over Rf. That's the first one. And the other one, because we have this open loop gain here, and so Vm and Vp are not equal, and according to the amplifier's definition, so Vo should be Vp minus Vm times A, which is open loop gain, or it's just called AV, equals to Vo. Another thing we know is Vp is 0. So for these three equations, can we get something from this? So let's take a look at this. If we label these three equations 1, 2, 3, then what we can do is Vp is 0, so we can definitely put it here. So minus Vm times AV equals to Vo, right? So now we can substitute Vm over here to get rid of Vm. So we only have Vm and Vo left over here. So let's try to get Vm first. Vm equals to minus Vo over AV, right? And then substitute Vm in the first equation. So we are getting Vi minus this guy, which is plus Vo over AV over R1 equals to Vm, which is this, minus Vo over Rf. Okay, now let's move forward with this conclusion for now. So what we can do is we can do a cross multiplication from the two sides. So we are getting minus Vo over AV times R1 minus Vo R1 equals to Vi Rf plus V over AV times Rf. That's what we have now. So keep in mind, the purpose is to get V over Vi, which is the voltage gain. And we have over here, three terms have Vo. So we want to move them together in one side. So minus Vo over AV times R1 minus Vo times R1 minus Vo AV Rf equals to Vi Rf. And combine this together, you take this minus sign out and take Vo out. So you are having R1 over AV minus R1 minus Rf, actually plus, because we are taking this minus sign out, over AV equals to Vi over R times Rf. So we eventually have these two terms being separated from all these terms. So Vo over Vi equals to minus Rf over R1 AV plus R1 plus Rf AV. Okay? Then what's going to happen? Look at this. Because AV is finite, right? So you cannot ignore these terms. So if AV is huge, what's going to happen? R1 AV will be 0 and RF AV will be 0 too. So you are getting the two zeros. You can cancel them out. So V over Vi eventually will be RF over R1. Okay. So that's why you do need an ideal or something close to ideal op-amps to be used for application. So you have a pretty accurate. You can get a more accurate closed loop gain whenever you connect the circuit like this. Otherwise, it's introducing these errors to the circuit, right? So what about the non-inverting counterpart? If the op-amps or the op-amp is being used is not ideal. A non-inverting counterpart, what's going to happen? Non-inverting. AV is finite. So let's look at this. VP, VM, Vin. VP is Vin, no problem. They are the same voltage node. First equation we can list. VP minus VM equal times A is VO, no problem as well. That's the definition of the op-amp. And here, that's the same current from here to here. So you know 0 minus VM over R1 equals to VM minus VO over RF. So the three equations should get you the result. But remember the strategy, right? So we want to substitute VM over here so we can have VO and VI being separated from each other. And let's see. VP is V in, so we can put V in here to substitute VP. And you can calculate VM from there, okay? So what you're getting is V in minus VM equals to VO over A. So V in equals to VO over A plus, no, VM, we're calculating VM, sorry, equals to, yeah, let's cross this one. So VM equals to V in minus VO over A, all right? And then you can substitute VM in here for the result. So let's do it really quick. I don't want to make this too long. So let's substitute VM in this equation. Use this one. Okay, let's do it. It will be 0 minus VM, which is V in V over A over R1 equals to V in minus VO over A minus VO over RF. And then do this. You are getting minus V in RF plus VO over A RF equals to V in times R1 minus VO over A R1 minus VO over times R1, and trying to separate all the terms have VO and V in. So definitely you can move things to here. We're getting VO RF over A plus R1 over A, which is this guy, and plus R1. For V in, you are getting R1 plus RF. So VO over V in equals to R1 plus RF over RF over A plus R1 over A plus R1. So this looks right. Then, if A is infinity, RF over A will be 0. R1 over A will be 0 as well. All right. Then what's going to happen is these two terms will be canceled. So VO over V in will be R1 plus RF over R1, which is the same as what we derived in the last lecture, which is a closed loop gain of the non-inverting amplifier using an ideal op-amp in the circuit. So that's why no matter it's a non-inverting topology or inverting topology, you do want to use the best quality of the op-amp, so you are getting the more accurate result for the closed loop gain. All right. Okay, so this is everything what we should cover for this lecture, and I'm going to see you in the next video. Okay.